they're there. Is that correct? Okay, good. Then our first speaker for the last session today is Jan. So.
Okay, can you hear me? Okay, well, I'm going to start talking anyway. So I changed the title slightly, but it's basically the same topic. I answered the question of the title in the abstract anyway. So 3 new tricks. One of them is sort of new. Another title for this could have been sort of a very academic project. So let's see. Okay, so this started basically as an informal collaboration where some of my colleagues were trying to find inhibitors for some protein. And it's not a secret what the protein is. I just can't remember what it is. And it doesn't really matter. It's sitting in the membrane. There's no X-ray structure. And when they started talking to us, they had been at it for 5 years. So basically, they is 2 groups, someone who does the measurements in the med school and a synthetic chemist who makes the molecules. And the start of this was an observation by a pharma company that this Cephalocast, which is a known marketed drug, also inhibits this protein they were interested in, sort of completely by accident. It's the mode of action for the actual medicine is very, very different. So it just happens to be an sort of okay inhibitor with a IC50 of 2 micromolar. And so they gave that knowledge to our medchem, or our medchem guy, and he sort of started the project. He's in the med school, so he can't make molecules, so that's where my chemistry colleague came in. And this has basically been something that isn't really funded, very typical academic project, trying to get something started with bachelor's and master's students. And then about a year ago, they scraped enough money together for a PhD. And so he had sort of been working, this PhD student had been working at it for a year when we joined. And so the sum of all this effort, 5 years effort, is about 100 indole-based molecules that they tested. And you can sort of see the histogram here of actives and inactives. Mostly they were unsuccessful. So the leftmost bar says less than 10 micromolar, but the best, they never found a molecule that's better than the Cephalocast. And the ultimate goal of this is to find something in the nanomolar range. That's when you can start applying for money and actually have a chance of sort of getting more than one PhD students on it. So that's what they want to do. What we basically try to do is just to get more actives, because there's not really a lot of sort of data here about activity. There's a lot of sort of censored data where the thing just didn't work. So we decided to do the best we could do with this is a classification model, and we settled on a cutoff of 30 micromolar for active and inactive. Okay, but if you actually then go look at the data set, you find that it's really sort of 2 groups of molecules. Most of them, the majority of them, is just derivatives of this Cephalocast molecule. And then you have some other indoles that don't really look like it. And these are just the actives I show you here, right? So by far, most of the actives that we saw before are just variations on a theme. So this is not a great data set. This is a very challenging data set to get started with. And this is actually what interested us. So it's challenging. So this sort of business as usual, I don't know about you, but the first thing we try is a random forest with Morgan fingerprints. That's sort of our go-to method. And so that doesn't really work. So what I'm showing you here is the predicted positives, right? That's that's how many we find. And on the x-axis, you just have this probability score that you get from the classifier model, right? Now, ideally, you want green on the right and red on the left, right? So a very clear division between the false positives and the true positives. And in fact, we get the opposite here. So we can't really make any predictions with this machine learning model. And the statistics here are based on leave one out, right? Because we don't really have enough data to make a proper test set and validation set. So, right, leave one out. You train on all the molecules but one. Can you predict this last one, right? And very often we fail. So this doesn't really work. Okay. So trick number one. So this sort of general approach it's kind of a data augmentation approach. We've used it for regression. And so I should mention okay, sorry. We had used it for regression. We knew how we would extend it to classification. So that would be the new trick, but it turns out it's actually published a couple of years ago. So it's actually very clever. So here are three very simple sort of model to illustrate it, right? We have three molecules, one active and two inactive. And so, of course, you can't train on three, but you can certainly train on 9, right? So we create the pairs, and then we have a classifier that says, basically, is this in the same category or not? So it's not whether the molecule is the same, it's whether it's in the same category, right? So the top molecule, that's the same. So that's in the same category, obviously. The next two molecules are in different categories, so they get a 0 and so forth. The main point is that you have 9 data points instead of 3. So if you have 100 data points like we did, right? So all of a sudden you have 10,000 sort of data points. Of course, they're not independent data points, right? But you really have a lot more points. So that's what you train your model on. When you then deploy it, so you have a new molecule, you want to know is it active or inactive. And so then you basically compare it to all the molecules in your training set. Okay? And so you'll get some number between 0 and 1, right? And so in this particular case, in the first case here, with the round molecule, you're comparing it to an active molecule, it gets a low score. All right? So the idea is there's a low probability that that's an active, so there's a high probability that it's an inactive. And then you do it for all pairs, right? You sum up the probabilities in each column, or take the mean, and then you simply look for the largest value. So in this particular case, you would predict that this molecule, the green molecule, is inactive because it's most similar, if you will, to the inactive molecules. And so if you do that, it's a little bit better now. So we don't have a perfect separation between the true positives and the false positives, but there is some separation. And so there's a reasonable cutoff, or there's a cutoff there where there's a reasonable chance that it's a true positive. So it's a leave one out. And so when we deploy it, this is fingerprints, for example. The way your descriptor for the pair is now the fingerprint of the first molecule, the fingerprint of the second, and then the difference between the fingerprints. So you have a longer descriptor vector. And so that's what you feed the model. So, okay, so we had a model that was reasonable, not great. And so then we said about, oh, that's not good. Yeah, I have a PDF version also.
Google Drive, and I think we can maybe open it as a PowerPoint.
Yeah, that's good.
Yeah. This is from recent various downloads. Yeah, it should be here. Oh, sorry, I clicked on the wrong one. I'll open folders, downloads. Yeah, here.
So the lesson here is that just because the first 4 slides look okay, doesn't mean the 5th slide looks okay. So
yeah, Let's first see if it shows.
Yes.
Yes.
Yeah.
Yeah, it does. Okay.
Oh, well, yeah, okay,
It doesn't?
not great, but let's go with it.
Yeah, okay. So now I'm gonna go to Zoom. Screen sharing meeting controls, and now share screen 2.
The slides are also on the Discord channel, so in PDF form.
Is that?
Yeah.
Sorry.
Okay, so we have this model. The first thing we tried it on is the enamine building block set, just because I had it lying around already. And in that, so this obviously only applies to indols because they're all indols. So we fished out all the indols. And on the left-hand side, we predicted 5 hits. And we then expected our collaborators to order these molecules and test them. But they decided, since they were relatively simple, they would make a great undergraduate research project. So they waited a couple of months and got some undergraduates to try to synthesize it. They could only synthesize one of them here with the 50 micromolar. And that's not active. But they made some derivatives of some of the other ones. And 3 of them were active. So it's not a real prediction. They sort of got the idea from our screen, but they didn't test the actual molecules we predicted. So, but they were happy. We were a little disappointed because we didn't really get our molecule tested. Okay, but then we screened another library. So this time we figured out how to download the enamine hit locator set, where there was about 7,500 indols. And here we actually did they made 2 models. So it's still this pairwise difference learning. But one model used fingerprints and the other one used a pharma2D descriptor set. And then we basically looked for molecules where both models predicted active hits. And so from those, we selected 11. They purchased this time, thank God, 10, but there were 0 hits. Okay, so most were just above these 50 micromolar. 3 you could actually get a value, right? But our cutoff is 30 micromolar. So that didn't work. Okay, so then we had to try something else. And while I was sort of working on this, I used they're all indols. When you look at them, like in the second slide, you want to align them on the indol. And and then when we did that and talked to our collaborators, they were sort of always talking about these different positions on the indol and what that might signify. And so that sort of gave me an idea for what I will call the 2D atomic pharmacophore model. So the idea is ultimately to make a sort of a better descriptor, hoping that the simpler models will perform better. So what does that really entail? First is you align. In this particular case, you just align on the indol. For more complicated molecules, you try to make a better alignment. Now you have 2D coordinates. And basically, you combine these 2D coordinates and cluster them. All right, so the indol will all have atoms in common. Some will have substitutions on different parts of this indol. You cluster them. You assign some arbitrary order to each cluster, and that gives you a descriptor vector. Okay, so the black axis here, that's the indol. They all have that in common, right? And then you have a descriptor vector where some of the positions will be 0. Okay, because there's no atom in this particular position, right? So you can make different descriptor vectors to sort of tell you at what site this molecule is substituted, right? And the atomic properties that we assign to these clusters are, one's just a presence. Is there an atom there or not? Is it a hydrogen bond donor? Or is it a hydrogen bond acceptor? So these are all binary. And then we also assign the atomic log p values that you get from the Crippen model, right? So the log p you predict with RD-KIT is the sum of atomic contributions. So we just took the individual contributions and assigned it to a cluster. And so you just concatenate these descriptor vectors. And so then when you want to deploy it, right, you again take your molecule, you align it, and then you make a descriptor vector. Now, there will be atoms there that are not sort of in your training set, and they will not get any position or any sort of entry in the descriptor vector, but that's fine because it has never seen an atom at that position in your training set. So it's appropriate that that's being ignored. So that's trick number 2, a new kind of descriptor vector, or at least I think it's new. When you actually deploy it on a large set, it gets a little more complicated, right? Because you won't have atoms at exactly the same spot when you sort of go away from the core. So you have to have all these things with a cutoff radius, what is closest to this cluster, how many examples do you need to consider it a cluster, and all this sort of stuff. Also, if a point is far away from the cluster and you sort of move it to the cluster centroid, we also scaled the property using some distance metric, right? So the further away you are from a cluster, the less it'll contribute to that cluster. And if it's too far away, sort of beyond another cutoff, then it won't contribute at all. So all this sort of fiddly stuff, with cutoffs and where do you put the cutoff and all this sort of stuff we did. Okay, trick number 3. So a general rule, if you have a better descriptor, you can usually get away with a simpler model. And so rather than making a random forest on this, we made a decision tree. So this is an actual decision tree that you can make to classify these 115 molecules into actives and inactives, right? So it's not very deep, and you can actually sort of make it understandable, right? And so we took sort of the decisions it made, and we're able to visualize it. Right, so the round things are log p values, right? So we're looking at this bottom node. So that's the one I show on the right-hand side, right? And so it thinks it's active because you need some hydrophobic or partly hydrophobic stuff, out by the bromine. You need some hydrogen bond donors in this region. You can't have a hydrogen bond donor, that's what the X is, or hydrogen bond acceptor here. So something you can sort of understand. Okay. And so because we have this limited data, when we pick our predicted actives, right? So we deploy this method on a library again. We get a lot of hits, but are they good hits? Well, now we can actually sort of see or interpret why our model thinks it's a hit or not, right? And what you really discover is that it's making these predictions based on really sort of tenuous reasons, right? And it's not because the model is bad, it's because the data set is bad. There's very limited information. But you at least you get some insight, right? So these 4 molecules on the bottom are actives in our training set. They're assigned to one node because they have basically 2 things in common, right? Some hydrophobic or partially hydrophobic stuff in 2 regions. So when you actually test it, so we made 12 predictions overall. They decided to purchase 11. 10 were inactive, so above 50, and 1 was an actual hit. Okay, so better than the previous one. Right, but we also, when we selected these 12, we could now select in different parts of the tree in order that we would learn something even if the compounds are inactive. And so I don't have, we now made a new decision tree by including these 11 new compounds, and it's now considerably deeper, which is good. Right, it has sort of more reasons to think something is an active or an inactive compound. And so the next step is to deploy that again on the same set and see if we get new hits. Okay, so even if you don't know what the protein is, so you don't care about it. But yeah, even if you don't care about this particular thing, right, at least maybe one of these new tricks, right, would be helpful, right? So that this pairwise difference, here is for classification. We've also used it for regression. That's in a paper here that just came out. One trick, there's a new kind of atomic descriptor. Now, it only works if you have a common core, but that's a reasonably, that occurs reasonably often in drug design. And sort of the general idea that if you really do have a good descriptor, right, sometimes you can get a lot of insight out of a simple decision tree. So that's it. Thanks very much for your attention. I'm happy to answer questions.
Thank you. So questions? Yes, over there.
When you think about strategies for the application, for example, translating the difference prediction more if the molecules are similar. In there are many ways to do it.
Yes. So the question is, have you tried all this, I guess, a little more complicated ways of deciding whether we trust a prediction or not? Is that fair to say? Like similarity measures, stuff like that. And so, I mean, the bottom line is no, we haven't tried anything but that implementation. But there's a lot of things you could try. Yeah. So it's a very sort of, in general, a very fruitful idea, I think, or idea to work on.
It would be the same of the information from pairs. You could have only 6 pairs.
Well, I think so. So for the training, you'll have a slightly different. Oh, sorry. Yeah. So the question was, you have basically 2 pairs of pairs, or two pairs, right, that are identical. The descriptor vector is not identical, right, because of the way we do it. Because we also take, so we'll have the first one first, the second one second, and then the difference, right? So when we deploy it, right, we only have, let's say, one example of each, right? And so the difference might matter. So it's best that the model has seen both combinations. Yeah. So I don't, you may not gain much by it, but I don't think you lose anything by it either. Yeah. Okay. So why not just use the difference yes, that's a yes, that's certainly one thing we should try. We use this simply because the original idea was a paper on regression. That's how they did it. And so that's why we did it that way.
So you said you were using Morgan fingerprints.
Yes. We used, in this particular case, the binary form. Yeah. Yeah.
Difference. It's useful to do the
Yes. Yes. Yeah.
Start with 2 chlorines, then you get a 1 chlorine, but the binary fingerprint has a 0.
Yes. Okay. So Greg's suggestion was to use the count fingerprint instead of the binary fingerprint. And yes, actually, now that you mention it, that's an excellent idea. Yeah.
Why do we have 9 first? And my question is, then during deployment, why do you have 3 pairs instead of 6? Because this new molecule go to the second one, right?
Yeah. And again, so, okay, the question was, we use both pairs in the training and one of the pairs in the deployment. Yeah. And yeah, so I sound like a broken record. That's what they suggested in the paper. And so that's what we did. And so again, so it's a very academic project. This is a bachelor student, running this on the side. It's unfunded. That's one. 2, they want to, they would like to purchase these molecules soon. We need to make a prediction soon. We don't, have time to try all different combinations. Yeah, but I think the main thing is that I haven't seen this used a lot or at all actually, and I think it's a very fruitful idea with a lot of different things one could tweak. So yeah.
You had one, yeah.
During this workshop, you spend a lot of like compare about 3 plus particles that maybe you working under that like people, for example.
Yeah, okay, yeah. So the question was, here we're just doing pairs. Can you do like triplets? And so I'm not sure how you would do that, right? Because in this particular case, it's just, you know, it's a binary classification. Is it in the same category or not? And so with triplets, I'm not sure how to do it right off the top of my head.
Okay, there is an activity triplet ways where the idea is to have anchor that is similar for the three molecules.
Sorry, to have a what? And then I'll do.
So one part is similar everywhere. And so there is an equation for that, for a triplet. It's called activity triplet.
Okay, so there's a suggestion to look something up called activity cliff triplets, and I will. Yes. Okay. So yes, and I can't remember what the prediction was. I think it was positive as far as I remember, but I'm not. But we did try it. Yes.
Very last. So, if it's only this, like, the typical place.
Okay. So yeah. So the comment is 3 molecules is very little. This was just to illustrate it. So, yeah, we tried it with 115. So the comment is it's a horrible data set you have, and I absolutely agree.